Hi, in the second section of Chapter 13 of Young and Freedman's University Physics, we get to a very important topic, and this is simple harmonic motion, abbreviated as SHM. So let's say you have a glider on a spring on a frictionless surface, and you stretch it, and you let go, boing, 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 boing. You know, if there were no friction at all, it would go on forever in theory. But, of course, there's always some friction and other things. But anyway, so that's simple harmonic motion. Think of a pendulum, you know, whatever you want to think of it. This is a very fundamental concept in nature. It's taken 13 chapters for us to get us here, but this will become important as we move forward in physics. Set some background. We might begin by remembering Hooke's law. I don't know if you remember Hooke's law from an earlier chapter. Might have been chapter 6. I'm not sure. Don't remember. But basically, Hooke's law is that force is proportional. In a perfect spring, force is proportional to displacement. The restoring force, if you remember from the video immediately previous to this, is the force that wants whatever it is that's going boing boing to return to its kind of resting state. The restoring force is the force. So the restoring force is always moving in the opposite direction of the displacement. So if you have a positive displacement, then the restoring force is negative, wanting to pull it back toward, you know, the zero. And if it's compressed, then the restoring force is positive, wanting to restore it to its starting point, but its displacement is negative. So the force and the displacement are always going to have opposite kind of signs. If the force is positive, the displacement is going to be negative. If the displacement is negative, the force is going to be positive. So basically, that's what you're looking at here. Now, when two things are proportional to each other, then all we have to do is find the right constant, the right multiplier or divider, and we can say that they're equal. And so K is a constant. You know, it's going to vary depending on the nature of the spring or whatever it is. So the constant there will vary. But for any kind of spring-like situation, the force is proportional to the displacement. It's going to be negative. It's going to be the negative of the displacement here, negative x, and then you multiply it by k, and voila, you have Hooke's law. F equals negative kx. Okay. So the constant's always going to be positive, but F and X are always going to have opposite signs. That's all I've been saying. All of that is somewhat review. So now let's talk about simple harmonic motion, which is what results if we then get things to boing, boing, boinging. So you'll remember that in this case F equals negative kx, but F also equals ma. So if we divide F by m and divide the other side, negative kx by m, then we get this, basically, that the acceleration in this spring situation is going to be negative kx divided by m, or negative k over m times x. And there we have a formula for the acceleration. And again, the acceleration and the displacement are always going to have opposite signs, because the acceleration is going to have the same kind of sign as the force, just because the force is just the acceleration times the mass. So if it's accelerating positively, then it's going to be on the negative displacement. If it's accelerating negatively, that's because it's on the positive side of the displacement. Okay, some various simple things, but there's our first new formula. A equals negative k over m times x, the acceleration of a spring. Now, I don't know who first did this. I should probably, but very clever. Whoever it was very clever. Simple harmonic motion is the projection. You can think of simple harmonic motion as the projection of uniform circular motion onto a diameter. So if you look in the diagram here, this is a diameter of the circle. I'm sorry, its picture was taken at somewhat of an angle, but in theory, that A should be right here. I'm sorry. But basically, this should be a diameter of the circle. And so then Q is a point going around the circle, and we're going to measure the circle in radian degrees, theta in radians, and omega is again the angular velocity, you know, going around this circle in radians per second, probably. So you can see that the x component, that if you shone a light here, the shadow, basically the shadow of this Q point going around the circle would look like a harmonic oscillator going boing, 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 boing. So as this goes here, this goes here. And as the Q goes around here, then this goes to here. And when Q hits here, it hits its negative amplitude, and it starts coming back, And so basically, if we cast a shadow from Q onto a diameter of the circle, we would have boing, 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 boing. We would have simple harmonic motion. And what is going to be the value of that point P on that diameter? It's going to be the A times the cosine of x. Using a little trig here, when you want to find the adjacent side, the cosine of an angle is the adjacent over the hypotenuse. So if we multiply the cosine of that angle by this radius, we're going to get whatever this p-value is. Isn't that brilliant, whoever came up with that? So we know here that x equals a times the cosine of theta, where a is the, basically, because the radius, you see the radius of the circle here is equal to the high amplitude, or the maximum value, maximum positive value of this harmonic oscillator. So what whoever came up with this has basically shown is that there is a very close relationship between simple harmonic motion and circular motion. So when you create a circle like this, we call the circle the reference circle, and this rotating vector we call a phasor. Long before Star Trek, there was this phasor here. The phasor is the rotating vector, like in a radar, sonar, whatever. Okay, so you can see this is why you may not have understood, I didn't understand in the first section, why angular frequency was denoted by omega, when I'd known that omega was angular speed earlier in the book. But now we can see that they really can more or less be conceptualized as the same thing, because the now, so let's go a little bit further. So if the acceleration of a spring, which we just found out was negative k over mx, is the same as the acceleration of circular motion, then we can begin to do a little algebra here. So we've just found out that the acceleration formula for a spring is negative k over m times x. Well, we know from a previous chapter, I think previous chapter 9, that the acceleration of a point on a circle is negative omega squared x. And again, if you go back and watch a video from, I think it's 9.3 or somewhere in there, if you want to know the derivation of negative omega squared over x, we can set these two equal to each other and solve for omega, and what we find is that the angular frequency, or angular velocity, whatever you want to call it, is equal to the square root of the constant for the spring, or whatever it is, divided by its mass. And so one of the interesting observations to that is that you can't make the angular frequency in a harmonic oscillator be what you want it to be. The angular velocity is a function of whatever the constant of the spring is, and whatever the mass of the, say, glider is. And so if you know the constant of the spring and the mass of the thing that's going in harmonic motion, then you're going to know what the angular frequency is. You can't determine it. It's determined by the properties of the thing in harmonic motion. Okay, in other words, it doesn't depend on the amplitude of the spring or whatever. Spring depends only on the constant and the mass. Okay, so there's our first kind of really important formula in this section. Omega equals the square root of the constant divided by the mass. Okay, now I'm going to end this video pretty soon because this is a lot, and have a second video to finish out the chapter. But before we do that, let's go ahead and talk about converting from angular frequency to a normal frequency. So you'll remember that angular frequency is in radians. So if we want to find frequency in cycles per second, we just divide the angular frequency by 2 pi, which is, of course, the distance around a circle, and we end up with a slightly modified version of the formula. Instead of it being the square root of k over m, it's 1 over 2 pi times the square root of k over m. And similarly, the period, that is, if the frequency is cycles per second, the period is seconds per cycle. It's the inverse of the frequency. And so basically we flip this equation. So instead of 1 over 2 pi, it's just 2 pi. And instead of k over m, it's the square root of m over k. And I'll stop there because that's enough, I think, for one video.